Okay, so why are some things soluble and others are not? If you're going to go take a shower and you had a diamond ring, you're not worried about it dissolving in the shower, right? But if you brought in like a big old thing of rock candy because, I don't know, you wanted a snack while you're showering and you got the thing wet, it's going to dissolve. Why? So that's what we're going to talk about in this section, like why things will dissolve, like what things affect that. So, boom. The really, really important thing of this whole entire lecture, this particular one is like dissolves like. So what that means is that polar solvents will dissolve polar things. Non-polar solvents dissolve non-polar things. So for an example here, right? So it's the intermolecular forces between the solute and solvent. They have to be strong enough to compete with those between like the pure solute and those that you have in the pure solvent. So the water, right? It has all these forces that are holding it together. It's got London, dipole-dipole, hydrogen bonding. This is sodium chloride. It's held together with ionic bonds. There's actually a fourth force you haven't learned about yet, but you're going to learn about it now. All right, so it's not really an intermolecular force, but it's a force. It's called the IonDipole force. All right, so, and it's really it's what it sounds like. It's a force between an ion and a dipole. So you have this polar molecule. That means it has two poles, a plus pole and a minus pole. So water is a very polar molecule, all right? So it can line up with the negative side facing all of the sodiums, and it can take its positive side and point that towards the chlorines, all right? This force is actually stronger than hydrogen bonding, right? And the ion-dipole forces are going to be comparable to the ionic bonds in sodium chloride, but there's also this added bonus of disorder, all right? We'll get to that in a later chapter, but creating disorder is a driving force in nature. So these particles, all the water molecules come in there and they like snaggle these little particles and they pull them off. They pull them apart, bring them out into the solution, and this is called solvation. So solvation is the process of the solvent dissolving the solute and just pulling it apart. If our solvent is water, we call this hydration. And my dog's having a nightmare behind me. We call it hydration, and we say the ions are hydrated. All right, so that's just specifically talking about water. All right. So if an ionic salt is soluble in water, that means it's because the ion-dipole interactions are strong enough to overcome the lattice energy of the salt crystal, right? If it doesn't dissolve, that means the lattice energy was too great. So if you go grab a rock from your backyard, right, that's basically just a big crazy ionic compound, most of them anyway, and you put it in water, it's not going to dissolve. You're not going to see it like a whoosh and disappear like it was a big old chunk of salt. Right? That just means the lattice energy was too great to overcome. Water's pretty crazy. We use water for lots of stuff. We call it the universal solvent because it dissolves so many different things. It dissolves molecular compounds, dissolves ionic compounds, acids and bases and stuff all are just totally happy in water, right? And so let's see. And here's sugar. This is I scoured the internet and found this picture, but it was like the same one that was actually in your book. So that's pretty cool. So this is just a sugar crystal. Sugar's got a bunch of these OH bonds, right? So bunch of things that have oxygen and then hydrogen sticking off of there. So there's lots of places for sugar to hydrogen bond. So water hydrogen bonds, sugar can do hydrogen bonds, so they'll mix. Right? And you see it dissolving right down there. Oil. Right? Y'all know that oil and water don't mix, right? That's because oil, the only intermolecular force it has going is London. Like oil is non-polar. So it doesn't do dipole-dipole, it doesn't do hydrogen bonding, it only does London. It's too different from water to mix with it. So remember, like dissolves like. All right, energetics. Ooh, there's some energy changes we're going to talk about. So there's actually 3 steps when we make a solution. You have to separate the solute, you have to separate the solvent, and then you put them together and you create the solution. So this is obviously a fictitious picture. We don't actually separate, the solute like that. We don't actually separate the solvent and then take those separated guys and put them together. But this is just to give you an idea of what's going on. The reason the solute is together is because there's intermolecular forces. That's what's holding this stuff together. It might be a liquid, it might be a solid, who knows? But it's being held together by intermolecular forces. So to move those things apart to make room for solvent particles, right, that takes energy. So this always takes energy. Separating these will always take energy. Same thing over here. Your solvent, right, to separate these particles, move them away from each other because they're attracted to each other with intermolecular forces. So to move them apart from each other, that takes energy. When you put these together and you form these new interactions, that releases energy. So this is uphill, downhill. All right, so this takes energy, but when you put them together, that releases energy. Another way to look at it is in a diagram like this. So you start off with like your solvent, your solute, right? It's going to take some energy to separate the solute. It's going to take some energy to separate the solvent. But when you put them together and form these new interactions, whoosh, releases energy. Cool. So if the third step releases more energy than the first two steps took, you're definitely going to make a solution. Right? It will definitely make a solution. If it releases, if it releases the same amount of energy that these first two steps took, it's still going to make a solution. In fact, if it releases slightly less energy, let's say it only releases like maybe this much energy, so slightly less energy is released than these first two steps took, it's probably still going to make a solution. That's because of the chaos stuff that I was telling you about earlier. So chaos and disorder, it's a driving force in nature. And so sometimes, even though energetically it's not getting all that energy back, the chaos will keep it going. All right, so that's kind of it for this thing. Big thing to remember is polar solvents dissolve polar compounds. Non-polar things dissolve non-polar things. So like dissolves like. All right, catch you in the next one.